Welcome to Chemical Process Safety. This video is about flashing liquids. This is a situation that would arise in the scenario where you have a chemical in your process that would normally be a vapor at atmospheric pressure. The classical example I like to think of personally is carbon dioxide because I used to work with that a lot in my research lab. And we would buy cylinders of carbon dioxide. And I didn't know this at first, but I learned after using it for so long that the carbon dioxide inside that vessel is actually a liquid. And this is oftentimes done if the chemical allows it, because a liquid will take up way less space than a gas. So for the same volume, you can fit a lot more material as in a liquid phase. So how this is done is that CO2 or whatever chemical it is pressurized, and just the act of pressurizing a gas will reduce the volume itself. But then when you condense it into a liquid, it takes up even less space. So that's advantageous. However, it's also potentially dangerous because in the situation where the vessel loses its integrity, so if a leak develops or a hole is punctured in the tank or whatever it is, and the pressure is lost, well, that liquid is going to begin to boil because, again, the boiling point of something that is a vapor is probably pretty low, the normal boiling point, that is. So, in the specific case where it's a flammable chemical that's being stored, like propane, for example, or liquefied natural gases, this can be explosive. And in the petrochemical industry and in the chemical industry, this is called a BLEVE. This is an acronym that stands for Boiling Liquid Expanding Vapor Explosion. There's a great video on YouTube that I'll link to down in the description that shows a BLEVE, a controlled BLEVE actually occurring, and that'll bring it to life. So go check that out whenever you can. So let's talk about the theory of flashing liquids. The heat that is available to vaporize the liquid is where we'll start. So again, we've got this chemical species that is being stored under pressure. And although the temperature outside or the temperature of that vessel is going to be greater than the normal boiling point, it is still going to be a liquid because the pressure inside that vessel is so high. But when that pressure is relieved, again, that relief of the pressure is going to cause the liquid inside to boil. So the expression for the heat available, I like to think of this as the excess energy, or the energy that the liquid has that is above the boiling point, is equal to m, the mass of the liquid, times the heat capacity of the liquid, times the quantity of T naught, the initial temperature, minus TB, or the normal boiling point. I can take that heat available and I can divide it by the enthalpy of vaporization. This is the amount of energy that is needed to vaporize 1 mole or 1 kilogram of substance. You got to be careful to match units here. So if we use mass there, we want mass here. So this is going to be enthalpy of the specific enthalpy of vaporization. So energy per mass. I can plug in my expression for Q. So take this expression and put it here, and I will get this following expression for MV. This is the amount of the vapor that, or the amount of the original liquid that will vaporize. It makes more sense to think about this in terms of the fraction vaporized. So it's possible that not all of it will vaporize if left to do its own thing. So here I'm just dividing by m, which is the overall. I like to, when I do this myself, I'd like to put a little L here to remind myself that this is the mass of the liquid, but that's also potentially confusing because once some of it starts to vaporize, you might think that the L is whatever's left over. But this M is the original mass that was in the tank before. This MV is the mass that will vaporize. So all I've done from this step to this step is I've just divided through by m, and that causes it to cancel. So far, so good, but there's a potential wrinkle here in that heat capacity and enthalpy of vaporization both might be functions of temperature. So as this thing boils, the temperature might decrease. So we have to account for that somehow. And the way that we do that is we can integrate, or we can turn this into a differential equation. So we could say dm is equal to mCp dt over delta HV. And this is a separable differential equation, so I could bring m over to the other side. So I'll take 1 over m is equal to Cp over delta HV dt. And the problem here is that this is tricky to integrate. So you might remember if I taught you an MEB, heat capacity could be a polynomial expression, and then delta HV can have many other forms as well. So one way to accomplish this integral is to take the mean value in the temperature range and then treat it as constant. So that's somewhat of an approximation that may be acceptable. So just for example, let's say the enthalpy of vaporization was 40 at T boiling, which may be 100, and I don't know, 60 at T naught. It would be 50, would be the average value. So you have to know what the value of the enthalpy of vaporization is at two temperatures, and then you take the average. That allows you to perform a somewhat easy integral, right? Because this comes outside of the integral. The integral of 1 over m is just ln of m evaluated at the limits, and we will get this expression. So I have to clean this up a little bit. So take the exponent of the entire thing, and when I do that, I obtain this expression. And this is not quite F. So M minus MV, that is the amount of mass that stays in the liquid form. So the other way to think about it would be M over M is 1. So this is 1 minus MV over M. So if I bring the 1 over to the other side and bring this over to the other side, I end up with 1 minus exponent of this whole thing. So there's an example that kind of illustrates what happens if you make this approximation versus if you don't. And we'll do it using water because even though water is not going to explode, right? Water can still flash, and losing containment of any chemical is generally a bad thing, particularly maybe if there's a hazardous component in this water. So let's say we're storing water in the saturated steam state at 350 Fahrenheit. If the vessel ruptures and the pressure becomes 1 atmosphere, find the fraction of water vaporized. So the way to approach this problem is to first recognize that we could look at the steam tables, and that will give us an exact answer. And then I will apply this equation, and that'll give me an approximate answer. So because I said the water was saturated at first, remember, saturated means that there is a saturation pressure that corresponds to this temperature. We could just get that by looking up directly in the steam tables what that pressure is. So I did this before I turned the camera on, and I found that pressure 1 was 134.6 psi. That was the particular steam table I used, is in these units. And I also have the enthalpy at that temperature as well. The final state is 1 atmosphere. That's the pressure outside. The normal boiling point temperature is 212. And I could look up what the enthalpy of the vapor and the enthalpy of the liquid is in those states. So just by a quick energy balance, delta H is going to equal 0 because there's no change in kinetic, no change in potential, and there's no work or nothing like that. So delta H has to equal 0, and therefore the final enthalpy is equal to the initial enthalpy. Enthalpy, this is enthalpy of state 1. H1 is 321.6 equals enthalpy of the liquid plus the amount of, or the fraction of the mass that evaporates times the difference in the enthalpy of the vapor minus the enthalpy of the liquid. So plugging some stuff in and crunching some numbers, I already have defined all these numbers up above. We get that the fraction of water that evaporates is about 15%. So keep this number in mind, and we'll compare using the formula that we had from above. So if we assume constant properties, so that's a worse approximation even, we're not doing the average properties, we can look these values up for water. So the heat capacity is 1.01 BTU per pound degree Fahrenheit, and the enthalpy of vaporization is 970 BTUs per pound. These are also values that are available in the steam table. So I can evaluate the fraction that will evaporate, and I will get an answer that is pretty close, not exact, but keep in mind that this is a much easier calculation, and if we can get the same answer by doing less work, that's not necessarily a bad thing. The more correct way to do it, or the one that's going to be closer to the true value, is assuming the average values. So once again, I'll look up the CP and the delta HV at the other temperature at 350, what the original temperature, and then I'll average those with the values that I got from 212. And then I'll plug them into my expression, and I will get that the fraction vaporized is still a little bit less than 15%. So in this specific case, the errors that we get by assuming either constant heat capacity or assuming average heat capacity are small. Keep in mind that this is not generally the case, and even though this may be acceptable to make these approximations, again, you should always be clear and state your assumptions up front, always. I'm not going to go through this. I think this is a little bit too detailed. There's going to be some more detail in the book if you're interested, but for now, I'm going to adjourn the video and I'll see you next time.